In this video, I will go over how to graph a logarithmic graph with shift, reflection, stretch, or shrink by starting with parent family and doing the add-ons. So let's look what a typical logarithmic graph looks like. So a logarithmic graph is pretty much the inverse of an exponential graph. So on this side, on the left, the one on the left, it's our exponential. And I just want to note out that with exponential, you have a y-intercept of 0, 1. And then you also have a horizontal asymptote at y equals 0. And then if you look at the other graph, this f inverse, this is the logarithmic graph. And as you can see, it no longer has an y-intercept. It has an x-intercept of 1, 0. So you kind of like switch the zeros and the 1 because they're inverses. And you no longer have a horizontal asymptote. You have what's called a vertical asymptote at x equals 0. Okay, so that's a logarithmic. This is an exponential, and this is a logarithmic graph. So let's talk about the characteristics. So just like an exponential graph, you do have an increasing and decreasing logarithmic graph. So how do you know if you have an increasing or decreasing? So when base is less than 1 but greater than 0, um, you have a decreasing. So yeah, the blue one is a decreasing because the base is less than 1 but greater than 0, and then the rest like log base 2. And if you look at ln x, why is it an increasing? Because ln x does have a base of 10. So right, so decreasing would look like the blue one, and then increasing would look like the green one or the red one, and they all have an x-intercept of 1, 0 unless there is a horizontal shift. Okay, so let's talk about the characteristics of a logarithmic graph. Usually it has an x-intercept at 1, 0 unless there's a horizontal shift. If there is a horizontal shift, your new x-intercept is 1 less from the horizontal shift. If the base is greater than 1, it's a logarithmic growth. So that just like on the previous slide, if the base is less than 1 but greater than 0, then it's a logarithmic decay. So like a fraction. Since the domain is no longer all real numbers, you must use the conversion y equals a log base a of x if and only if a to the y equals x. So just unlike like exponential um, linear graphs, you could put any kind of input. You could put, because the domain is all real numbers, you could put any, for example, y equals 3 raised to the x, right? Because the domain is all real numbers, you could plug in any x. But since logarithmic graphs are not all real numbers, there are some restrictions, and you can't just use any x values. Right, so you're going to have to use this conversion. So go ahead and write this down. Okay, so y equals log base a of x if and only if a to the y equals x. Domain is usually at 0 to infinities, right? So you usually can't use a negative x value. So your domain is usually from 0 to infinity unless there was a horizontal shift. And then this time the range is all real numbers. So the y value will be all real numbers. Okay, so I will explain the conversion when we start graphing. So how do you graph a logarithmic graph? You would write down everything you know about the logarithmic graph. For example, if you list any horizontal, vertical shift, reflection, etc. Pick three coordinates from the parent graph and do the add-ons. I will explain. You must use the conversion y equals log base a of x if and only if a to the y equals x to find the 3 points of the parent graph. If you have a horizontal shift, then your new vertical asymptote is always it's always one less from your horizontal shift. So if you have a horizontal shift, your new vertical asymptote is always one less from the horizontal shift. And I'll explain when we do graphing. So let's look at example one. Example one says graph the following logarithmic graph, completely determine domain and range. So in example one, we have f of x equals log base 4 of x. So just like the exponential graph, write down everything you know about this graph. So if you look at our base is 4. And what does that mean? Is that a growth or a decay? It is a growth. Does it have a horizontal shift? No. Does it have a vertical shift? No. Um, what else do we know? We have an x-intercept at 1, 0. Because that means our vertical asymptote is at x equals 0. Okay, so what I'm going to do is we could just this is our parent family since it is there's no horizontal shift, no vertical shift. We know that our vertical asymptote is at x equals 0 because there's no horizontal shift, and that also means we have an x-intercept of 1, 0. So how do you plug in points? So we can't just use any x values we want. Our domain would be from 0 to infinity. So I'm going to plug in, I'm going to try 1. My x value is 1. So f of 1 is log base 4 of 1. So remember it's on the notes, we have to use the conversion y equals log base a of x if a to the y equals x. Okay, so if I plug in the a value, my x value 1, so we have this right now. We got to make it look like this. So this is like saying when you plug in 1 into the function, you get log base 4 of 1. So that's equivalent to saying 4 to the what power gives you your x value, which is 1. So 4 to the what power gives you 1. That would be 0. So your y value, because yeah, your y value will be 0. So your y value will be 0. Okay, so when you plug in x value of 1, your output is 0. And then if you plug in 2, you get log base 4 of 2. So that is so I'm plugging in 2 because you would get 4 to the what power gives you 2. That would be 1/2, right? 4 to the 1/2 gives you 2. So your y value is 2. So your coordinate will be at 2, 1/2. And then my next X value will be 16. I don't want to really deal with like decimals right now, but you can use, because our domain is from 0 to infinity, you can use 3. And here, I'll show you, I'll plug in 16 and then I'll plug in 3 to show you um, both works, but why I wouldn't use 3. So if I plug in f of 16, it would be log base 4 of 16. So that's like saying 4 to the what power gives you 16? 2, right? 4 to the second power gives you 16. So your y value is 2. So your coordinate of this would be 16, 2. Okay? So we have 3 coordinates already. Now, can you use the x value 3 if you wanted to? You could use x value 3, you could use 4, you could use 5, because our domain is from 0 to infinity. Yes. So what if I did want to do 3? It's not going to come out as, it won't be, it would be like a weird decimal. So here, I'll show you. So if you plug in 3, you get log base 4 of 3. So you have to use the conversion. So log base 4 of 3 is equal to saying 4 to the what power gives you 3. Okay, so there's no number. There's no number that'll give you, it's impossible, right? There's no number when raised gives you 3. So what you have to do is take the log of both sides. So on the right, it would be log of 3. And then on the left, if you have an exponent and you want to expand it, you put the power in front of the log. So it would be y log of 4. Okay. And then you would solve for y. So you would divide this by log 4. Log 4. So you get y equals log 3 over log 4. Okay. Now you have to put this in the calculator. Log 3 over log 4 is, it's about 0.79. So if you plug in 3 for your x, you're going to get an output or a y value of 0.79. Okay, so go ahead and start graphing. So our vertical asymptote is at x equals 0. My first coordinate would be at 1, 0, right? When you plug in 1, you get an output of 0. That's also our x-intercept. Our next one would be at 2, 1/2. There's 1/2 would be right about here. And then the next one would be 16, 2. So let's pretend this is 16. Our graph is not in scale, and then here's 2. And then it's going to look something like this. Okay, it's slowly increasing, and then it's going to go down like this, but never crosses the vertical asymptote. Okay, it says determine the domain and range. So the domain is from 0 to infinity, and then the range is all real numbers. Okay, go ahead and copy, and then we'll move on. Example 2 says graph the following completely determined domain and range. So let's write down everything we know about this graph. So is there, oh, okay, so let's look at the base 3. The base is 3, so we know that is technically a growth. Uh, +2 is a vertical shift of 2 units up. This negative is reflection across the x-axis. So there are a few things that's going on. So we do have to start with the parent graph, right? Okay, so what would be our parent graph? Our parent graph would be y equals log base 3 of x, right? So let's find 3 points from this graph. So if I plug in 1, this is like saying log base 3 of 1, which is like saying 3 to the what power gives you 1. That would be 0. So you have a coordinate at 1, comma 0. And then what other x values that I should use? I guess I could use 3. You could use 2, but it'll be decimal, so I'll do 3. So log base 3 of 3. So this is like saying 3 to the what power gives you 3. That'd be 1. So this would be 3, comma 1. Okay, and then the next x value I will use 9 because I won't deal with decimals. So this will be log base 3 of 9. So this is like saying 3 to the what power gives you 9. 2, right? So you have a coordinate at 9, comma 1. I mean 9, comma 2. Okay, so these are your coordinates, and then we'll just do the add-on. So the next one, I'm going to do the reflection across the x-axis. So it's going to be y equals negative log base 3 of x. So what does this negative do? What you do is you pretty much multiply the y coordinate by this invisible -1. So 1, comma 0 will still be 1, comma 0, because if I multiply the y coordinate by -1, it'll be 0. 3, comma 1 would be 3, comma -1. And then 9, comma 2 would be 9, comma -2. Okay, lastly, the other one is the vertical shift. That's easy. So what this +2 means, you just add 2 on the y coordinate. So 1, comma 0 will be 1, comma 2. 3, comma 1 would be 3, comma -1 would be 2 minus 1 is 2. 9, comma -2 would be 9, comma 0, right? Okay, so now time to graph. So we have no horizontal shift, so our vertical asymptote is x equals 0. And we have one, then just plot the point 1, comma 2, 3, comma 2. Is that right? 3, comma, this is wrong. -1 plus 2 is +1. That's wrong. Okay, so 3 comma 1, and then 9 comma 0. Let's pretend this is 9 somewhere here. Okay, connect the dots and make sure it doesn't cross the vertical asymptote, so it's going to look something like this. Okay, and just make sure it doesn't cross, so this keeps on going up. So what would be my domain? My domain would be still from 0 to infinity, and then my range is, what is my range? All real numbers. Okay, go ahead and copy. And then we'll finish up with the next two examples. So let's just make it all in one video. So let's do example 3. We have log base 10 of x over 10. My base is 10. So let's write down everything we know. If you want, you can, this graph is also equivalent to saying log base 10 of 1/5 x, right? So this is equivalent to that. So we know that the base is 10, and we also know it's a growth. And what else do we know? This 1/5, I'm not sure what it does. I mean, I know it's related to the horizontal because it's near the x. So it's not a horizontal shift. It's either a horizontal stretch or a horizontal shrink. I forget because I don't know all the rules, but what I do know is um you're gonna multiply the x coordinate not by 1/5, but the reciprocal 1/5 by 5, because horizontal is always opposite. So yeah, that's it. So no horizontal shift. So that means our vertical asymptote is still at x equals 0. And what else? Um, yeah, that's it. So let's start with the parent graph. So what is our parent graph? Our parent graph is y equals log base 10 of x. So let's plug in 1. That's log base 10 of 1. So that's equivalent to saying what's 10 to the what power gives you 1? 0, right? 10 to the 0 is 1. So you have a coordinate at 1 comma 0. And then let's plug in 10. Log base 10 of 10 is 10 to the what power gives you 10, that'd be 1. You have a coordinate at 10 comma 1. And then I'm going to do I'm going to do 20, but it's not going to come out nicely. It's going to be a decimal because I don't want to. I mean, I could do 100, but you would have to. Um, Yeah, okay, so if let's do 20. So log base 10 of 20. So this is like saying 10 to the what power gives you 20? Nothing, right? There's no, you cannot change the base. So what you do is take the log of both sides. So on the right, it's going to be log of 20. On the left, you're going to do the power, so it's y log of 10. And then solve for y, so you're going to divide this by log 10. Okay, so you get y equals that. Just put that in the calculator and you will get about 1.3. That's 20 comma 1.3. Okay. Now what I would do is let's do the 1/5 x. So like I said, what you're gonna do is you're not gonna multiply the x coordinate by 1/5. You're actually gonna multiply the reciprocal of 1/5, 5. So 1 comma 0 will be 5 comma 0. 10 comma 1 would be 50 comma 1. And 20 comma 1.3 would be, if you multiply the x value by 5, 20 times 5 is 100 comma 1.3. Okay, so go ahead and graph it. So our vertical asymptote is at x equals 0. Okay, so let's see. There, our graph is not going to be in scale, so we're going by 5, 10, 15. Let's go by 20, 10, 20, 30, 40. No, how about, what should we do? We should go by 5, 10, 15, 20. Yeah, this would be 20. Let's go by fives. 5, 10, 15, 20, 25, 30, 35, 40, 45, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100. Perfect. Okay, so we're going by fives. So 5 comma 0 would be 1, 2, right here. And then 50 comma 0 would be 40, 45, 50. I mean 50 comma 1. And then 100 comma 1.3 would be right about there. And that's your graph. What would be the domain? The domain would be from 0 to infinity. And then the range would be all real numbers. You go ahead and copy. Example 4, graph the following logarithmic graph, completely determined domain and range. So we have log base, this should be a base 10 right here. So log base 10 of x minus 1. So what do we know about this graph? The base is 10, so we know it's a growth. This x minus 1 is a horizontal shift of 1 unit to the right. So that means our vertical asymptote is not 0 anymore. Our vertical asymptote is going to be at x equals 1. So let's start with the parent graph y equals log base 10 of x. So if I plug in 1, I get log base 10 of 1, which is 10 to the what power gives you 1, 0. 1 comma 0. And then if I plug in 10, this is like saying 10 to the what power gives you 10, 1. And then maybe I'll do 20. So this is like saying 10 to the what power gives you 20. It doesn't come out nicely, so you're going to have to take the log both sides. This is log of 20. This is y log of 10. And that's about 1.3. Okay, and then we can just graph the final one. The horizontal shift. So what this means is you just add 1 to the x value, right? So 1 comma 0 will be 2 comma 0. 10 comma 1 would be 11 comma 1. 20 comma 1.3 would be 21 comma 1.3. Okay, let's start graphing. Okay, so let's kind of descale this. Let's make these by 1. So 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So 2 comma 0 would be 2 is right here. 11 comma 1 would be, there's 11. And then 21 comma 1.3 would be increasing. And then we said our vertical asymptote is at x equals 1. 1. So if this is 1, it would look something like this. So what would be our domain? it would be from parentheses 1 to infinity. And then my range is all real numbers. Okay, so that is the last example, and the next video will be quiz.